To determine the appropriate size inverse times circuit breaker for the feeder supplying the motors, we will follow Article 430 of the National Electrical Code, or NEC. Firstly, we need to identify the full load current for each motor. According to Table 430.150, a 15 horsepower 460 volt motor has a full load current of 21 amps. A 10 horsepower 460 volt motor has a full load current of 14 amps. A 75 horsepower 460 volt motor has a full load current of 96 amps. The 75 horsepower motor operates on a 15-minute intermittent duty cycle. According to 430.22 paragraph E, we can apply a correction factor of 85% to the full load current. Therefore, the adjusted full load current for the 75 horsepower motor is 96 amps multiplied by 0.85, which equals 81.6 amps. Secondly, according to 430.52, we can size the inverse time circuit breaker at 2.5 times the full load current of the largest motor. In this case, that's the 75 horsepower motor with an adjusted full load current of 81.6 amps. Multiplying 81.6 amps by 2.5 gives us 204 amps. We round up to the next standard breaker size, which is 225 amps. Thirdly, according to 430.62, we need to ensure the feeder has sufficient capacity to carry the load of all motors. We sum the full load currents of all motors and add them to the breaker size we previously determined. That's 225 amps plus 21 amps plus 14 amps plus 14 amps, which equals 274 amps. Since we need to select the next size down, we will use a 250 amp inverse time breaker. Thus, a 250 amp inverse time breaker is required for the feeder supplying the specified motors. To calculate the service load for the commercial building, we'll consider the loads for both tenants. We will follow the guidelines in Article 220 of the National Electrical Code. Firstly, let's calculate the general lighting load. According to 220.3 paragraph A, we multiply the square footage of each tenant space by 2 volt-amps per square foot. Tenant 1 has 5,100 square feet and tenant 2 has 23,300 square feet. So, we calculate 5,100 plus 23,300, which equals 28,400 square feet. Then we multiply that by 2, resulting in 56,800 volt-amps. According to 215.2 paragraph A, we then apply a diversity factor of 1.25 to the general lighting load. Multiplying 56,800 volt-amps by 1.25 gives us 71,000 volt-amps. Secondly, let's calculate the show window lighting load. According to 220.12 paragraph A, we multiply the length of the show window by 200 volt-amps per foot. Tenant 1 has 12 feet of show window lighting and tenant 2 has 50 feet. So, we calculate 12 feet plus 50 feet, which equals 62 feet. Multiplying 62 feet by 200 volt-amps per foot gives us 12,400 volt-amps. According to 215.2 paragraph A, we then apply a diversity factor of 1.25 to the show window lighting load. Multiplying 12,400 volt-amps by 1.25 gives us 15,500 volt-amps. Thirdly, let's calculate the kitchen equipment load. According to 220.20, we have two 1500 volt-amp microwaves and two 12-amp refrigerators. So, we calculate 2 multiplied by 1500 volt-amps, which equals 3000 volt-amps. We calculate 2 multiplied by 12 amps. This equals 24 amps. 24 amps is multiplied by 80%. This equals 19.2 volt-amps. 3000 volt-amps plus 19.2 volt-amps equals 3019 volt-amps. We will use 3019 volt-amps. Fourthly, let's calculate the receptacle load. According to 220.3 paragraph B, we count the number of receptacles and multiply by 180 volt-amps each. Tenant 1 has 24 duplex receptacles and tenant 2 has 45 duplex receptacles. So, we calculate 24 plus 45, which equals 69 receptacles. Multiplying 69 receptacles by 180 volt amps each gives us 12,420 volt amps. Fifthly, let's calculate the water heater load. We have two 4,000 volt amp water heaters, so the total water heater load is 4,000 volt amps plus 4,000 volt amps, which equals 8,000 volt amps. Sixthly, let's compare the heat and air conditioning loads. According to 220.21, we omit the smaller non-coincidental load. The total heat load is 20 kilowatts plus 120 kilowatts, which equals 140 kilowatts. The total air conditioning load is 25 amps multiplied by 240 volts plus 28 amps multiplied by 240 volts, which equals 12,720 volt amps. Since the air conditioning load is smaller, we omit it and use the heat load of 140,000 volt amps. Seventhly, let's calculate the multi-outlet assembly load. According to 220.3 paragraph B, we have 40 feet of multi-outlet assembly in tenant 1, 40 feet in tenant 2, and an additional 20 feet simultaneously used. So, we have 1440 volt amps plus 1440 volt amps, and the 20 feet simultaneously used is 3,600 volt amps. 1440 plus 1440 plus 3,600 volt amps equals 6,480 volt amps. Eighthly, let's calculate the arc welder load. According to 630.11 paragraph B, we have two 32 amp welders at 100%, one at 85%, one at 70%, and 25 at 60%. So we calculate 2 multiplied by 32 amps, which equals 64 amps. Then we have 32 amps multiplied by 0.85, which equals 27.2 amps. Then we have 32 amps multiplied by 0.7, which equals 22.4 amps. Then we have 25 multiplied by 32 amps multiplied by 0.6, which equals 480 amps. The total amperage is 593.6 amps. Then we multiply that total amperage of 593.6 by 71%, which equals 421.45 amps. Ninthly, let's calculate the motor load. We have a 2 horsepower 120 volt motor, a 10 horsepower 120 volt motor, a 5 horsepower 120 volt motor, a 1/2 horsepower 120 volt water pump, and a 10 horsepower 240 volt motor. Their respective amperages are 24 amps, 100 amps, 56 amps, 9.8 amps, and 50 amps. 24 plus 100 plus 56 plus 9.8 plus 50 equals 239.8 amps. Finally, let's sum all the loads. We have 71,000 volt amps for general lighting, 15,500 volt amps for show windows, 3,000 volt amps for signage, 4,704 volt amps for kitchen equipment, 12,420 volt amps for receptacles, 8,000 volt amps for water heaters, 140,000 volt amps for heat, 6,480 volt amps for multi-outlet assemblies, 421.45 amps for welders, and 239.8 amps for motors. Summing all these loads gives us a total service load of 1482.48 amps. To determine the feeder load in amperes for the multifamily dwelling using the optional method, we will follow 220.32 and 220.33. Firstly, let's calculate the general lighting and small appliance load. Each unit has 1,800 square feet of living space, and there are 4 units. According to 220.3 paragraph A, we multiply the total square footage by 3 volt amps per square foot. So, we calculate 1,800 square feet multiplied by 4 units, which equals 7,200 square feet. We multiply 7,200 square feet by 3 volt amps per square foot, which equals 21,600 volt amps. Then we add the small appliance load of 1,500 volt amps per unit for 4 units, which equals 6,000 volt amps. So the total general lighting and small appliance load is 21,600 volt amps plus 6,000 volt amps, which equals 27,600 volt amps. Secondly, let's calculate the appliance load. Each unit has a 13 kV amp range, a 0.6 kV amp disposal, a 1.2 kV amp dishwasher, and a 12 amp 120 volt compactor. For 4 units, the total range load is 13,000 volt amps multiplied by 4, which equals 52,000 volt amps. The total disposal load is 600 volt amps multiplied by 4, which equals 2400 volt amps. The total dishwasher load is 1200 volt amps multiplied by 4, which equals 4800 volt amps. The total compactor load is 12 amps multiplied by 120 volts multiplied by 4 units, which equals 5760 volt amps. So, the total appliance load is 52,000 volt amps plus 2400 volt amps plus 4800 volt amps plus 5760 volt amps, which equals 64,960 volt amps. Thirdly, let's compare the air conditioning and heat loads. Each unit has two 18 amp 120 volt air conditioners and a 2.5 kV amp 240 volt heater. The total air conditioning load is 2 multiplied by 18 amps multiplied by 120 volts multiplied by 4 units, which equals 17,280 volt amps. The total heat load is 2500 volt amps multiplied by 4 units, which equals 10,000 volt amps. Since the heat load is smaller, we omit it. Finally, let's calculate the total service load. We have 27,600 volt amps for general lighting and small appliance load, 64,960 volt amps for appliances, and 17,280 volt amps for air conditioning. Applying the demand factor of 45% from 220.32, we multiply the total load of 109,840 volt amps by 0.45, which equals 52,128 volt amps. Dividing 52,128 volt amps by 240 volts gives us a total service load of 217.2 amps. Thus, the feeder load for the multifamily dwelling is 217.2 amps. To determine the feeder load in amperes for the 120 over 240 volt 3-wire service using the standard method, we'll follow Article 220. Firstly, let's calculate the general lighting and small appliance load. Each unit has 1700 square feet of living space, and there are 13 units. According to 220.3 paragraph A, we multiply the total square footage by 3 volt amps per square foot. So, we calculate 1700 square feet multiplied by 13 units multiplied by 3 volt amps per square foot, which equals 66,300 volt amps. Then, we add the small appliance load of 2 1500 volt amp small appliance circuits per unit for 13 units, which equals 39,000 volt amps. So, the total general lighting and small appliance load is 66,300 volt amps plus 39,000 volt amps, which equals 105,300 volt amps. According to 220.11, we apply a demand factor to this load. We take the first 3,000 volt amps at 100% and the remaining 102,300 volt amps at 35%. So, we have 3,000 volt amps plus 102,300 volt amps multiplied by 0.35, which equals 38,805 volt amps. Secondly, let's calculate the range load. According to 220.19, we have 13 units with 12 kilowatt ranges. Using column C of table 220.19, the demand factor for 13 ranges is 28,000 volt amps. Thirdly, let's calculate the appliance load. According to 220.17, each unit has a 1500 volt amp dishwasher and a 600 volt amp disposal. So, the total appliance load per unit is 1500 volt amps plus 600 volt amps, which equals 2100 volt amps. For 13 units, the total appliance load is 2100 volt amps multiplied by 13, which equals 27,300 volt amps. We apply a demand factor of 75% to this load, so we multiply 27,300 volt amps by 0.75, which equals 20,475 volt amps. Fourthly, let's compare the heat and air conditioning loads. Each unit has a 2.5 kV amp 240 volt heater and a 23 amp 120 volt air conditioner. The total heat load is 2500 volt amps multiplied by 13 units, which equals 32,500 volt amps. The total air conditioning load is 23 amps multiplied by 13 units multiplied by 120 volts, which equals 35,880 volt amps. Since the heat load is smaller, we omit it and use the air conditioning load of 35,880 volt amps. Finally, let's sum all the loads. We have 38,805 volt amps for general lighting and small appliance load, 28,000 volt amps for ranges, 20,475 volt amps for appliances, and 35,880 volt amps for air conditioning. Summing all these loads gives us a total load of 123,160 volt amps. Dividing 123,160 volt amps by 240 volts gives us a total service load of 513.16 amps. Thus, the feeder load for the 3-wire 120 over 240 volt service is 513.16 amps. To calculate the load and the building feeder for the duplex using the standard method, we will follow Article 220. Firstly, let's calculate the general lighting load. According to 220.3 paragraph A, we multiply the square footage of each unit by 3 volt amps per square foot. Each unit has 1900 square feet, and there are 2 units. So, we calculate 1900 square feet multiplied by 2 units multiplied by 3 volt amps per square foot, which equals 11,400 volt amps. Secondly, let's calculate the small appliance load. According to 220.16 paragraph A, we have two 1500 volt amp small appliance circuits per unit for 2 units. So, we calculate 2 multiplied by 1500 volt amps multiplied by 2 units, which equals 6,000 volt amps. Thirdly, let's calculate the laundry load. According to 220.16 paragraph B, we have 1500 volt amps per unit for 2 units. So, we calculate 1500 volt amps multiplied by 2 units, which equals 3000 volt amps. The total general lighting, small appliance, and laundry load is 11,400 volt amps plus 6,000 volt amps plus 3,000 volt amps, which equals 20,400 volt amps. According to 220.11, we apply a demand factor to this load. We take the first 3,000 volt amps at 100% and the remaining 17,400 volt amps at 35%. So, we have 3,000 volt amps plus 17,400 volt amps multiplied by 0.35, which equals 9,090 volt amps. Fourthly, let's calculate the range load. According to 220.19, we have two 9 kilowatt ranges. Using column C of table 220.19, the demand factor for 2 ranges is 11,000 volt amps. Fifthly, let's calculate the appliance load. Each unit has a 5 amp disposal, an 11 amp dishwasher, and a 3 kilowatt hot water heater. So, the total appliance load per unit is 600 volt amps for the disposal plus 1320 volt amps for the dishwasher plus 3000 volt amps for the water heater, which equals 4,920 volt amps. For 2 units, we multiply 4,920 volt amps by 2, which equals 9,840 volt amps. We apply a demand factor of 75% to this load, so we multiply 9,840 volt amps by 0.75, which equals 7,380 volt amps. Sixthly, let's compare the heat and air conditioning loads. Each unit has two 20 kilowatt heaters and three 3 horsepower 240 volt air conditioning units. So, we calculate 2 multiplied by 20,000 volt amps multiplied by 2 units, which equals 80,000 volt amps. The total air conditioning load is 17 amps, as per 430.148 multiplied by 2 units multiplied by 240 volts, which equals 8,160 volt amps. Since the air conditioning load is smaller, we omit it and use the heat load of 80,000 volt amps. Finally, let's sum all the loads. We have 9,090 volt amps for general lighting, small appliance, and laundry load, 11,000 volt amps for ranges, 7,380 volt amps for appliances, and 80,000 volt amps for heat. Summing all these loads gives us a total load of 107,470 volt amps. Dividing 107,470 volt amps by 240 volts gives us a total service load of 447.79 amps. Thus, the load on the building feeder for the duplex is 447.79 amps. To calculate the load on the building feeder for the duplex using the optional method, we will follow 220.33. Firstly, let's calculate the general lighting load. According to 220.3 paragraph A, we multiply the square footage of each unit by 3 volt amps per square foot. Each unit has 1900 square feet, and we are considering 3 units for this calculation. So, we calculate 3 units multiplied by 1900 square feet multiplied by 3 volt amps per square foot, which equals 17,100 volt amps. However, this calculation seems to be based on 3 units, which is incorrect. The answer should use 2 units as stated in the original prompt. As such, there is an error. We will correct it by taking 2 units, and will solve for the correct amount based on that. So, we calculate 2 units multiplied by 1900 square feet multiplied by 3 volt amps per square foot, which equals 11,400 volt amps. Secondly, let's calculate the small appliance and laundry load. Each unit has 1500 volt amps for small appliances and 1500 volt amps for laundry. For 3 units, we have 3000 volt amps plus 1500 volt amps, which equals 4500 volt amps. We are going to correct this as well. Taking into account the 2 units instead, the calculation would look like such, with each unit having 1500 volt amps for small appliances and 1500 volt amps for laundry. For 2 units, we have 3000 volt amps plus 1500 volt amps, which equals 4500 volt amps. Thirdly, let's calculate the appliance load. Each unit has a 9000 volt amp range, a 600 volt amp disposal, a 1320 volt amp dishwasher, and a 3000 volt amp water heater, with the units being incorrectly stated as 3 in the answer, which is a mistake. This should be only calculated for the 2 units that it is intended for. As such, let's fix the amounts here to reflect the 2 unit total. With these changes, the appliance load calculations will be 9000 volt amps multiplied by 2 units, which equals 18,000 volt amps. 600 volt amps multiplied by 2 units, which equals 1200 volt amps. 1320 volt amps multiplied by 2 units, which equals 2640 volt amps, and 3000 volt amps multiplied by 2 units, which equals 6000 volt amps. We are going to have to also recalculate the grand total. The total appliance load is 18,000 plus 1200 plus 2640 plus 6000, which equals 27,840 volt amps. Fourthly, let's compare the heat and air conditioning loads. Since the air conditioning load is smaller, we omit it and use the heat load of 120,000 volt amps based on 3 units, but that is another incorrect amount. Each unit has 2 20,000 volt amp heaters, and the answer said to omit the AC since it is smaller, so we will not include it in the grand total. A new heat load calculation is required. 2 multiplied by 20,000 volt amps multiplied by 2 units equals 80,000 volt amps. Finally, let's calculate the total load. We have 11,400 volt amps for general lighting, 4,500 volt amps for small appliance and laundry load, 27,840 volt amps for appliances, and 80,000 volt amps for heat. Applying the demand factor of 45% from 220.32, we multiply the total load of 123,740 volt amps by 0.45, which equals 55,683 volt amps. Dividing 55,683 volt amps by 240 volts gives us a total service load of 232.1 amps. The building feeder in the duplex is 232.1 amps. To determine the motor feeder demand load in volt amps for the specified service, we will follow Article 430. Firstly, let's identify the full load currents for each motor. The provided information includes single-phase and three-phase motors with varying horsepower and voltage ratings. We need to convert the horsepower ratings to equivalent amperage values for each motor. We also must take into account the intermittent duty ratings. For the single-phase motors, we have a 115-volt 5-horsepower motor with a nameplate current of 46.8 amps, a 230-volt 7.5-horsepower motor with a nameplate current of 33.2 amps and a 5-minute intermittent duty rating, and a 230-volt 10-horsepower motor with a nameplate current of 41.5 amps. For the three-phase motors, we have a 460-volt 7.5 horsepower motor with a nameplate current of 9.13 amps, a 460-volt 20 horsepower motor with a nameplate current of 22.41 amps and a 5-minute intermittent duty rating, and a 460-volt 40 horsepower motor with a nameplate current of 43.16 amps. We must adjust the amperage values for the motors with intermittent duty ratings. According to 430.22 paragraph E, we can apply a correction factor of 85% to the full load current. Therefore, the adjusted full load current for the 230-volt 7.5 horsepower motor is 40 amps multiplied by 0.85, which equals 34 amps. The adjusted full load current for the 460-volt 20 horsepower motor is 27 amps multiplied by 0.85, which equals 22.95 amps. To determine the motor feeder demand load, we need to apply a demand factor to the largest motor. According to 430.24, we take 125% of the full load current of the largest motor and add it to the sum of the full load currents of the remaining motors. The largest motor is the 115-volt 5-horsepower motor with a full load current of 56 amps. So, we calculate 56 amps multiplied by 1.25, which equals 70 amps. We then add the full load currents of the remaining motors, which are 34 amps, 50 amps, 11 amps, 22.95 amps, and 52 amps. The total amperage is 70 plus 34 plus 50 plus 11 plus 22.95 plus 52, which equals 239.95 amps. The feeder demand load is 239.95 amps, which requires a number 250 copper THWN conductor.